Yes, so today I'll be talking about vulnerability of power systems, and particularly from the perspective of short-term voltage stability and system strength. I work at TU Delft in the Department of Electrical Sustainable Energy and the group Intelligent Electrical Power Grids. As I mentioned, I work with Professor Marian Popov and Professor Jose Rueda Torres. I'm also part of a bigger project that I will briefly discuss, and we work with several industry partners in the Netherlands, and also abroad, mainly with TSOs and DSOs, but also with General Electric, the Metrology Institute of the Netherlands, etc. So what am I going to be talking about today? I have quite a lot of slides. I don't know if we're going to make it through all of them, but let's see how far we get. So first, quick introduction. I'm going to just have a couple of slides on the project that I'm part of. Then I'm going to move on to the, let's say, main topic today, short-term voltage stability. And first, I'm going to be talking about the impact of distribution networks on short-term voltage stability. Then I'm going to move on to a different topic, but very related, which is system strength. And there I'm going to mainly talk about classification, how we can evaluate system strength, and some challenges that still remain. And in the end, I'm going to be talking about more from a quantification perspective of short-term voltage deviations. So let's start a bit with a very quick introduction. So Vladimir already said I come from Netherlands. Netherlands is a quite small country in Europe, but very populated with almost 18 million people right now. And TU Delft, as you see here, is located between Rotterdam and Hague. And I work at the Delft University of Technology, which is the oldest and largest Dutch technical university. I think as of this year, we're 180 years old with 26,000 students and more than 3,000 PhDs. And TU Delft is almost every year ranked amongst very highly amongst the engineering and technology universities worldwide. So in Netherlands, there is a long history of harvesting wind energy. If you look at centuries ago, even typical Dutch windmills were there to harvest the energy of the wind and use it to let's say, tame the rising waters in the Netherlands. And if you move to more modern times, there is a huge amount of offshore and onshore wind energy being installed all over the Netherlands and off the shores of the Netherlands in the North Sea. This is one of the wind parks that is already in operation, but there are many more. So if you look at the plans of the Netherlands in terms of renewable energy, particularly here offshore, this here on the left is the coast of the Netherlands, and here we see the proliferation of offshore wind energy, which is currently on several gigawatts. By 2030, the plan is to have more than 20 gigawatts. So we have a really exponential rise in wind energy, particularly offshore wind energy, and this is something that is really affecting power systems already, and we can only imagine how it is going to affect power systems if we already see effects here, how it is going to be at this point, which is only 8 years from now. Except from offshore wind, we also have a lot of onshore wind, which is also increasing a lot. Here it is in blue, and PV and solar, which is another very large source of electricity in the Netherlands already, and is also going to increase a lot over the coming years. In terms of energy, by 2030, the plan of the Netherlands is to cover more than 70% of the electricity demand with the PV and wind. So we see very big increase, and the goals are shifting more and more towards the renewable penetration, and also with current situation in the world with the gas and oil prices, this is even becoming more emphasized and accelerated. I like to call this likely the biggest evolution or revolution in electrical power systems, probably since we have them at the first places they were, let's say, invented by Nikola Tesla. But this new revolution is as well bringing some challenges, and we as electrical engineers need to figure out some ways how to deal with them. So what are some of these challenges, particularly the dynamic ones that I'm going to talk about today, that we see with so many renewables? If you look worldwide, let's say first with Europe, we already see several larger events happening lately. For instance, we had a system separation in Europe, which is operated as a single system, but due to faults, we had not one but several system separations lately out of step conditions, which threatened to cause blackouts in certain parts of the continent. If we look at Australia, which is also known for having very high amounts of renewable energy, they also had several big events, such as the 2016 South Australian blackout, where they had a rapid frequency voltage collapse and instability, and I think more than 1 million people were without electricity for several hours. If we look at the other events that we see oscillations occurring worldwide, from China to US, UK, also in Europe, in Germany, we saw something with offshore wind energy. Furthermore, in UK as well, there was recently an event where a lightning strike quite far away from an offshore wind farm caused the wind farm to trip, and that kind of cascaded and caused 1 million people to be in dark for some time. And what we also see in the US, for instance, which is very interesting, is that a lot of renewables are not complying that well with forthright true conditions, and that we see due to that some more risks of cascading. So, for instance, if you go to the NERC website, you'll see a lot of disturbances that have that kind of effect. So there are a lot of challenges that we see, and we are still in some way at the beginning of the energy transition. So we can only imagine how this is going to escalate in the next decade or two. So if we think about this in terms of risk in power systems, these events that I just talked about used to be low probability, high impact events, but that is rapidly changing. We see much more frequent events like these. We see them happening faster, which we see them happening with the more enhanced deviations in voltage and frequency. And the question that we come to is, how can we better evaluate these vulnerabilities of the system and maybe be proactive about this and be ready once they start occurring even more regularly in the system. I'm going to give a couple of slides about a bigger project that I'm part of, RESIDENT. So RESIDENT stands for Resilient Synchro Measurement Based Grid Protection Platform, and it is a project led by Professor Marian Popov, but we have a lot of people involved into it. And the motivation of the project is very much in line with what I was just talking about the challenges that we're dealing with controlling future electric power grids, particularly in terms of reduced system resilience, in terms of inertia and system strength. And except for utilizing the known methods and the known ways of handling and tackling these events, we're also looking into applying modern measurement units across the system, such as phasor measurement units, also some SAS sensors that we have in the Netherlands, and combining them into wide area monitoring approach, but also wide area monitoring, protection and control applications. So we have several working packages in this project. First one deals with developing a platform for testing all of these applications. Second one deals with some machine learning and AI methods for detection, localization, and classification of disturbances. We have another work package on controlled islanding to derive a method for coherence identification of generators and detecting out-of-step conditions and doing some sort of a controlled separation of a system and not allow system to split in the way that let's say it wants, but we could do it in a controlled manner to avoid blackouts and have the separate islands that will operate stably after the separation. And in the end, we have the grid vulnerability and cascading events work package, which is on developing algorithms for vulnerability assessment. If you want more information about this project, that we recently had a paper in Paris, in SIGRE. I think that's a very good overview of things we do. You can probably find it online. It's also on ResearchGate if you cannot find it on SIGRE. And there we have some more information about all of these topics that I mentioned. So I'd like to start with this. What is actually grid vulnerability, and what do we want to focus on here? This definition is one I say like the most, and I think it's the most accepted one, as vulnerability is defined as the risk level presented by power system during a specific static or dynamic operating condition, particularly regarding the occurrence of cascading events. So it is the risk level regarding the occurrence of cascading events. And in that sense, vulnerability is an essential indicator of proximity of system collapse. So with all this shift to renewables, why and how are systems becoming weaker? Why do we need to think about this more than we used to in decades previously? So it all comes back to synchronous generators in a way. Since we are reducing the number of synchronous generators and instead putting inverter-based resources, on one side we have lower inertia because of the ability of synchronous generators that had to store kinetic energy in their rotating masses. We're losing that ability with installing inverter-based resources, and that low inertia causes frequency issues. But on the other side, we also have another effect, which is somewhat less talked about or explored maybe, but also becoming more and more a very relevant topic. That is that we get also lower system strength, which I'm going to talk about what exactly it is, and that is more related to voltage issues. So if we think about system strength, which I'm going to be mainly focusing on today, that is very similar to what inertia is to frequency, system strength is to voltage issues. So as we see number of IBRs increase in power systems, the importance of this right side is also increasing, as IBRs fundamentally rely on stable voltages too. So if we look at the current practice in the industry, we have a lot of ways to evaluate inertia, and then also different ways that we can evaluate frequency deviations directly, so we can try to preserve system stability in that sense. On the other hand, what we need to do, and should do more in the future also, is how we can evaluate system strength, so we can predict voltage issues, and on the other hand, the issues themselves, how we can evaluate them. As I like to put it here, is how do we evaluate the symptoms or voltage deviations or instabilities directly. So I'll be more focusing on this part today. So first, I'm going to talk here about impact of distribution networks on short-term voltage stability. First, a quick definition. This is actually from the joint working group that Vladimir mentioned, that is now in press, and I think it should be published, I think early next year, which works with the voltage stability assessment in transmission systems. So short-term voltage stability, sometimes also known as transient voltage stability, but that term is not that used that much anymore, involves dynamics of fast-acting load components, induction motors, electronically controlled loads, HVDC links, and inverter-based generators. And that's an instability that occurs typically under 10 seconds. It is very similar to rotor angle instability in a way, or converter-driven stability, but I'll talk about a bit more later. So what do we see in terms of changes in distribution systems? In distribution systems, the biggest change we see is the penetration of distributed energy resources. And if you look at it from the perspective of increasing penetration of DERs, if you have very low number of or amount of DERs, you typically do not see any problems in terms of your operation of the system, and it's easily accommodated. As the number increases, you start to see some limitations. Typically, first in distribution network itself, you see some short circuit levels being decreased or increased. You see some protection coordination issues, maybe power quality issues, occasional over voltages. As you increase DERs more, you start to see some issues on transmission level as well. You see some congestions occasionally. You see voltage control and voltage stability potentially challenges. And once we reach a very high amount of DER penetration, which is something that we're inevitably going towards, we see that the core duties of bulk power system operation become very impacted by DERs, and that is not just about reverse power flows or congestions, but we can see system balancing issues, we can see stability issues, restoration, and many more things that come with that. So DERs and distribution systems are becoming much more impactful in the overall system operation, resilience, and stability. Except for these changes in distribution systems, we also have change of dynamic loads and also electronic loads that have been more and more applied throughout power systems. So we used to have distribution systems that were very simple to model and simple to analyze, and we could predict very well what they would do in various operation scenarios. However, this is changing rapidly, and we see much more complexity there. And it's also interesting that these two changes are occurring in places in the system where system is generally not very strong, not that much system strength in a way, or that much grid itself. And these two effects can also be what I call a positive feedback. So dynamic load increase can also result in more issues with the operation of DERs and vice versa. And that's something also I'll be talking about. We did one case study in the southwest part of the Netherlands, where we have a lot of renewables, a lot of solar, a lot of wind, also offshore wind, and we see their grid operators are seeing much more dynamics occurring in the grid, and they're having trouble following and understanding what those dynamics are, where those dynamics are coming from, and how we can control them and maybe avoid them with, and not let them cause some cascading issues. So for instance, in this part of the grid, we also have installed PMUs. So not only on transmission system, but in this case on distribution system on 50 kV level, there are PMU measurements to try to pinpoint what is happening with these dynamics that we occasionally see with the large penetration of renewables on distribution level. One study here we did was to model part of this distribution grid. So that distribution grid comes here on 50 kV level and is connected further on the transmission level. And we modeled one part of it in Power Factory. And the goal of this study was to really model the distribution part, the loaded part, as detailed as possible, and see how that affects the results compared to typical models that we see being applied in distribution systems. So to model the grid, we use the real data of the grid. We use the best available data we have on DERs, because that's also sometimes an issue. You don't have all the information. You need to assume some things about renewables on distribution system. We use detailed controls using some standardized models. We also applied low voltage ride-through requirements that are valid in the Netherlands, and the rest of the grid is represented by voltage sources. And then we subjected this grid to faults and recorded dynamic responses to see how these different variations of load or load composition affect the stability and performance of the system. So I have here one of the results where we looked at how can voltage trajectory behave after a fault. And what we did is we had the same P and Q in the distribution system, but we have very different load compositions in different scenarios from 1 to 5, where we started first with very simple load models, and then we moved to more detailed and more accurate load models to see what can change. And here I have, if we look at the pink line, we have here an event where a fault causes some kind of stalling in motors due to the rapid drop of voltage. Current of motors increase, so we see a bit of a effect that on the voltage. We see here a part of our DERs or renewable energy sources which do not have to comply to a low voltage ride-through disconnect, depending on when they were installed and their size. Further on, we also have some combined heat and power plants here that as well have low voltage ride-through requirements up to a point. And in this case, we modeled where it would happen that they also they also drop after a certain voltage event. And furthermore, we get even more DERs to drop. And what we get in the end is basically a very different operation of the system with these load models or these active distribution network models compared to if we just did a very simple load and negative load for renewable generation. So what was let's say the main goal of this exercise was to show that if we were to just model the distribution network using static load models and very simple renewable energy models like negative load, etc., the results we will get for post-fault voltage behavior will be very, very inaccurate. And with that in mind, we went and expanded that study. We went much broader to not have only one small distribution system, but we went for a big IEEE system. So we used IEEE test system for voltage stability studies, which is one of the latest models developed by IEEE, and it's very useful for advanced voltage stability studies. And the model itself contains all the dynamics, all dynamic controllers and models that we need to model these kind of events. And we also see a lot this model being utilized nowadays in the academia and industry. And the model itself is quite realistic as it is based on the Nordic system. So what we did with that model, we wanted to, let's say, improve it further and make it more relevant for these studies of impact of distribution system on short-term voltage stability. So first what we did is we added some dynamic loads there. So if you think about old type of load modeling, that would be basically this. Instead, we moved to this model from US from VEC, composite load model, which has several different motor types. We have motor types from A to D. They represented different types of motors in the grid. We have electronic load, static load. We also have DERs there that we will represent later. And this allowed us to have much more accurate dynamic response. And we can also play with different variations of this of these penetrations of different types of the load and see how that influences voltage stability. Except from that, we also added a lot of DERs to the system. So in a similar manner, but this time using the known DERA model, which was also very recently developed as a model, which is much more accurate in representing behavior of distributed generation compared to previous models that were available. And it's also very much tweakable, that we can play with different parameters and determine how different control strategies of DERs, such as voltage ride through, such as blocking or disconnection, etc., how all of them affect system conditions. And particularly here we focused on short-term voltage stability. So we started with this model. As it has very simplistic load representations, we decided we're going to enhance it. So we added a lot of more advanced load models in the central area, which is most voltage instability prone area. And we also add a lot of DERs in that area. Furthermore, because we're dealing here with a lot of complexity, we decided to do this in a more automatized way. So we created a Python script to connect all of this in Power Factory, that we can simulate large number of scenarios better and faster. So we use the Python to allow us programming access to Power Factory, all the modelless variables. We could use very fast variable handling, case scenario changes, data processing, and of course automatic scripting. So what did we want to find out with this research? First, we want to find out how do loads and their composition particularly affect dynamic response of larger systems. We wanted to find out how important is it to model these things more precisely. So can we use very simple models, and if not, why? What effect does a large number of DERs have on transmission system stability? How do different control algorithms of DERs affect voltage stability? What is the combined effect of DERs and dynamic loads? And finally, what are the bottlenecks that we might see in future grids in terms of short-term voltage stability? So first, with dynamic load, we did the study with 11 different dynamic active distribution network models, basically. In this case, without DERs, just load models. We varied their composition, we varied their mounting percentage, fault location, and all of that we did automatically in Python to evaluate short-term voltage stability for each scenario. And then we created results in sort of a heat map, so we can visualize more clearly what is happening. So this was one of the results from that. So what we did here, we did more than 1,320 simulations and organized them in a heat map, where we have on x-axis you have increased penetration of dynamic load relative to static load. On y-axis you have different compositions of loads, so different types of motors having more presence in the grid, and the colors indicate the number of unstable cases out of the 12 different faults that we simulated in the system. So what these results show is that dynamic loads play a quite important role in voltage stability. So if you look at case 0, which is all static loads, we see that there is basically no instabilities happening in the system, regardless of which faults we apply. However, once we start moving towards different types of dynamic loads and we start to increase their penetration, we see more and more instabilities appearing in the system. And we also see some patterns happening there. We see, for instance, that type D motors, which are motors designed to replicate single-phase air conditioning, have quite a big impact on short-term voltage stability, and that is something we know also happens, for instance, in the US with their fault-induced delayed voltage recovery issues, but also elsewhere. We also see some other interesting patterns, like that motors of type A and type C are less related to instabilities, more related to instabilities compared to motors type B, and we see which penetration percentages start to cause issues. So we can tell roughly that once we reach 30 or 40% of dynamic load, that we might be experiencing issues in post-fault voltage deviations. Furthermore, this is just an example how one of those, if we take one of these 8 results, we have in each result we have a dynamic simulation of a short-term response, and we evaluate that in terms of short-term voltage stability, record everything, and then see if we can find a pattern in which factors play the most role in instabilities. Furthermore, we introduced DERs to see how will that affect the response. So the main methodology here was similar. So we would introduce advanced DER models, the ones I discussed before, and these distribution systems that we have in the central area. We would change their amount, we would change their control and parameters, again, different fault locations, and similarly, we create a heat map for visualization. In terms of controls, it is very important to keep in mind that different control strategies of DERs can result in very different dynamic behavior of DERs. So in other words, control can matter a lot. We modeled 4 types of control of DERs. First, we modeled very simple DER strip in case of a large fault occurs, which is something that we probably don't want to see in the system anymore, but it still happens a lot, as I mentioned in the beginning. Then we modeled ride-through with 2 different control strategies, prioritizing Q or P. And then we also modeled momentary cessation or inverter blocking, where the inverter, after fault, temporarily stops injecting active power, which is blue in this line, and slowly ramps it up after the fault. So what kind of results did we find once we combined DERs with the dynamic loads, and how does that impact voltage stability? Here particularly we looked at ride-through, at two different control strategies for ride-through. We looked at Q priority and P priority. And similarly as before, we made a heat map. Here we have different types of load composition, and here we have different penetration of DERs from 0 to 10% relative to the system load. And we saw that introducing DERs is positively affecting short-term voltage stability. And we see even if you start with 0%, you have a lot of instabilities occurring. However, if you increase DERs that respond by supporting the grid during the fault, number of instabilities reduces very rapidly. So in that sense, we can say that DERs are positively affecting short-term voltage stability. However, system response here is heavily influenced by the control we apply, as I'll show on the next slide. So here we see that Q and P priority control support is very positive. So we can say that this is a good effect from DERs in terms of short-term voltage stability. However, if you look at some different control strategies, so if you look at DER stripping, you will see that they don't basically change the base case where we have a lot of instabilities. More DERs don't make it better. Instead, they even make it worse. So what this right heat map is showing, basically, if we have a different penetration of DERs, and we have DERs that have more ride-through or tripping. So here is all the DERs are tripping, and here all the DERs are riding through. What we see that the more penetration of DERs we have, and the more of them are riding through, the better the response becomes of the grid. And what is interesting also, we see that partial tripping is about 2 times more detrimental than equal grid supporting ride-through. Or in other words, for each megawatt of DER that we lose that trips after fault or during the fault, the system would need roughly 2 megawatts of voltage supporting DER to compensate for that effect. And we see that here. So we need, if we have 8 DERs that ride through and 3 DERs that trip, then only then we start to see things balancing out. If we look at the similar numbers here, we see that the ride-through generators are not able to compensate for the tripping of DERs. So it is, we show here that it's very detrimental for the system short-term voltage stability if DERs were to drop during or after the fault. So to summarize a bit, what are the most important findings of this research? We had several research questions that we want to tackle that I mentioned in the beginning. So first, how do loads and their composition affect dynamic response? We see that higher presence of dynamic loads negatively affects short-term voltage stability, and we see that especially in types A and C, which are low inertia motors, and we see that also on D-type or single-phase AC units. On second, how important was it to model loads more precisely in these studies? We found that it is very important, since dynamic response can drastically change. What effects does a large number of distributed generation have on transmission system stability? We find there that DER can be both positive and negative effects, so it really highly depends on the control strategy in the end. You cannot make a general statement about how DERs affect short-term voltage stability. It really matters about how they are controlled. And how do different control algorithms actually affect this? we found that if the ERs do not ride through the fault, their effect is very negative on short-term voltage stability. However, if they do ride through, and if they have grid support, they can be very positive in terms of their effect. And what kind of effects did we see in combined increasing load complexity in DERs? We saw that voltage excursions are becoming more enhanced, and they can be detrimental to the overall stability. And then, of course, it highly depends on the type of load, type of DER control, and the penetration we have, and also grid strength, something I'll talk about a bit later. So we really need to be careful about how we model these active distribution networks, and how we make statements about which type of active distribution network affects voltage stability in what way. It will really come down to the type of the loads, type of the DERs, penetration of each, and controls being applied. And we also found that some of the bottlenecks might be that increasing amount of dynamic load plus DER without advanced monitoring, control, analysis can be potentially very problematic, especially if you apply very simple models, make analysis based on that, and expect systems to behave in a stable manner that may be very different in reality. I'll move now a bit on a slightly different topic, but very related, which is system strength. So I'll talk about classification, some evaluation, and challenges. So if you ask worldwide, how do we define system strength? That is a difficult question. It varies. So the known way to define system strength was short circuit capacity. However, that is changing. We see, for instance, from the Migrate project, we see a definition that says that system strength is a short circuit capacity at near nominal voltage, but not representing the fault behavior. We already see there confusion arising with short circuit capacity defining not fault behavior. Furthermore, we see National Grid defining system strength as the ability of the system to remain stable during and following disturbances in two factors, both inertia and short circuit capacity. We see NERC from the US defining system strength as the sensitivity of voltage to variations of current. We see AEMO from Australia defining it as the size of the change in voltage following a fault or disturbance. And we also see a different definition lately, which is the ability of the power systems to maintain and control the voltage waveform during both steady state operation and following disturbance. So there is no consensus in industry or academia what exactly system strength is. It is in a way all of these things, but we want to make it more consolidated. So,
but, Aleksandar, just to interrupt you now, when we say, we in electrical power systems, we know very well the term infinite bus.
yes.
Infinite. Can you just give a few words about what infinite bus is, and just to relate to all these plethora of definitions and very interesting approaches? So,
So infinite bus
would be useful.
Yeah, infinite bus will be basically a bus that if you try to inject some current towards that bus, it would not really affect the voltage because the bus has so much short circuit capacity that the voltage sensitivity is basically zero. So you would assume that the voltage sensitivity, maybe this definition is closest to that. The sensitivity of the terminal voltage would be basically zero or very, very low.
But not only voltage, also frequency.
Yeah, which is here I focus on voltage, but of course you would assume there that inertia is also extremely high, let's say, so you cannot change it.
What is the short circuit capacity of infinite bus?
Yeah, it depends. It will be infinite.
Infinite, exactly. What means that if we create an equivalent model of infinite bus, it is a source with zero impedance and output voltage which is the same like the voltage of the source. What means that that's exactly in line of your sensitivity. There is no sensitivity. There is no voltage drop. What means whatever happens in the grid, this voltage is always 1 per unit.
Yeah, that is true. But I'm going to talk more about why such an assumption and such, let's say, way of looking at system strength is maybe not super applicable for the future. I agree that is, of course, a strong bus, but it is questionable how much we can use the concept of strong bus anymore.
Brilliant. That's very nice. I'm quite excited. Thank you.
So I like to put here what is system strength, some analogies about it. So if you look at system strength for perspective, if you have a system, let's say, which is a rock or a jelly, and you look at network system strength for that perspective, if you would gently touch a rock, very little would happen, and other people in touch with that rock would not notice that, if it's of course a gentle touch. However, if you do the same with a jelly, you will notice wobbles throughout the whole system. So everyone would notice the variations happening. So what is also interesting is that if more people would try to stop these variations, it may cause further variations. So it would be very hard to synchronize between those actions. And if we go back to power systems, here we will have an analogy that rock would be a very strong system, jelly will be a very weak system, and the people that I mentioned will be different sources connected to the system. Another nice analogy for this is a trampoline, where we have a strong system and a weak system. And basically, a strong system would be like a trampoline that has many springs. So if some variation happens, if someone jumps, the movement will be very slight and it's easy to keep the balance. However, a weak system would be like a trampoline that doesn't have many springs. So if someone makes a disturbance, in this case we talk about voltage fluctuations, it will be very hard to keep the balance. And it will get even harder as other IBRs in this sense, or people in this analogy, would try to damp those oscillations. Again, it will be hard to synchronize those things well. And further problem is that some IBRs may trip or fall off, and then you have even further disturbances happening. So in this sense, springs would be system strength. And in our case for power systems, those would be synchronous generators. So how do we approach this system strength versus system stability? If you think of system stability, we have 5 different classes of it. In 2004, we had these 3: rotor angle, voltage stability, and frequency stability. However, with proliferation of renewables, 2 new were added a couple of years back. And where do we fit system strength into this? We know it's not type of stability, but what is it related to all of this? So power system stability and system strength are related very much, and we can think of system strength as voltage resilience. So system strength is a measure of voltage resilience, same as inertia is a measure of frequency resilience. The more of it we have, the less of variations we would expect given the same change in the system. And system strength primarily determines susceptibility to voltage instability. So more system strength we have, the less likely voltage instability is. But we also need system strength for some other things in the system, such as control interactions between IBRs, power quality, protection, etc. Because yes, if we have reduced system strength, we will also likely have reduced fault currents, and then we have potentially protection coordination issues as well. In conventional systems, as me and Vladimir talked about now, this was well captured by short circuit capacity. But if we have converter-dominated systems, that might not be the case anymore, because I will give some equations later, but because our very approach in defining short system strength and our usage of Thevenin equivalence is no longer that applicable. So how can we evaluate system strength? The very, let's say, common and the basic way to do it is to have Thevenin equivalence. You have IBR, you have some kind of a short circuit impedance, and then you can calculate voltage at this bus via the Thevenin equivalent. If you add a small deviation in voltage, in current, you will have a small deviation in voltage, and you can easily calculate from there that the sensitivity of that change is directly related to the short circuit impedance. You can also see that that is very related to short circuit capacity, and you can easily conclude that short circuit capacity is inversely related to the short circuit impedance, and that is related to the sensitivity. So the more short circuit capacity you have, the less of your voltage to current sensitivity is, and vice versa with the grid impedance. So the common way was to simply calculate short circuit ratio, which would be short circuit capacity divided by the power of your IBR or any other change in systems that you might have experienced. And you would say, okay, if this value is above 3 or something, depending on the system and depending on the application that you're looking at, we have strong enough system. Otherwise, we might have some issues with weak systems. However, we already see a problem. What if this IBR is not just one IBR? If we have more IBRs? One approach is to use a weighted approach. This is something that Texas does in their grid. So you kind of find a weighted sum of all the IBRs and short circuit strengths in the system. But then if you do this, you're instantly assuming that all IBRs are operating at the same bus and that their interactions are, they fully interact with each other. You ignore the impedances between them in the grid. So if you want to account for the actual grid impedances, you can also do that mathematically, and you can calculate the so-called site-dependent short circuit ratio, where you can calculate exactly how would these different IBRs affect the short circuit capacity. However, even if we do that, there are still some challenges and still some things that remain and emerge. So if you think about static challenges or steady state challenges of these methods, if we come back to this example, they are not always fully representative of actual system strength because of several things. First one is they don't take into account any of these things. They don't take into account local load. So if you have a load here, short circuit ratio doesn't reflect that in any way. But that load will very much affect how weak your system is. Because if you have very high load here, that will kind of locally take a lot of this power, that power will not go further towards the system, and you will not have that power being injected into the let's say weak system. So more load would increase your system strength there, but you don't see that with your methods. Furthermore, we don't look at the ratio of reactance and resistance. And that is also something that can affect the strength of the system. We don't look directly at what voltage we're operating at, and if we have some support there in terms of FACT devices, or we have synchronous condensers, etc. And what is also important, we don't look particularly at small signal stability. We more focus on static voltage stability, but we do not look at can this source maintain small signal stability also. Some of these challenges can be addressed by using voltage sensitivity metric, which is something that is a new method for looking into system strength. But again, not all of these, and we still need to think that some of these methods need to be improved to evaluate static system strength accurately. Some other dynamic challenges that we see of these methods. So most of the stuff I talked about now was on steady state. Now, if you think about dynamic state, grids are becoming very nonlinear in dynamic state. So if you remember the Thevenin method that we apply here, it really relies on the grid linearity assumption. So if we want to create this model, we must assume that this is linear. However, we know that IBRs are not linear in the post-fault period. And that is mainly the consequence of IBRs having limitation in maximum current during faults, limitation in different control strategies that are being applied, and the different intensity of the fault or disturbance will change the grid impedance. So this impedance is no longer constant. It is a function of the fault and a function of the control of IBR. So this basically no longer becomes applicable if we talk about dynamic sense. Furthermore, we also have large signal stability issues. We can have faults that may lead first to post-fault weaker grids. For instance, if we lose an important line or an element, we have more disturbed voltages and frequencies because of everything I discussed before with the inertia and system strength. And we also have higher IBR penetration that leads to larger phase voltage jumps and higher rock-off. And we see those effects particularly being problematic for PLL, and PLL is not able to keep up with the precise measures of system frequency, system voltage angle, and that we can see again affecting large signal stability. And that again you don't see in your short circuit ratios. And one IBR, even if it has a larger short circuit ratio, can be less stable in terms of dynamic operation. Furthermore, we also see some maloperation or unintentional disconnections. So if you look at protection, we see much more issues with protection not being able to operate as it should. It can misoperate or even maloperate. That is something I work, for instance, in my master thesis, but it's also a very, very popular topic nowadays with protection misoperation in high renewables operation. We see a lot of IBRs and DERs which may not ride through, as I talked about in the previous topic, and even if we assume that they will support the grid, maybe they will not, and that can also especially happen if we have voltage dynamics by dynamic loads, and we see both of these concerns being enhanced with less system strength. So what I want to say with this slide is the systems can be simultaneously strong, steady state, but weak in dynamic state, or vice versa. So we really need to think about system strength in both dynamic sense and steady state sense, and look at it from those two different perspectives.
Aleksandar, that's a fantastic thing which you have in this slide. Point 1 and point 2. Let's just see. Point 1 is, please just judge what I'm gonna say. Point 1 is one problem.
Yep.
Point 2 has to do with the design of controllers of, for example, type 4 generator. In this controller, there is something what is called phase lock loop.
Mm-hmm.
If we have a fault, if we have disturbances, if we have distortions, these distortions will affect the phase lock loop and make it operating wrongly.
Correct.
What means the role of phase lock loop is, for example, to measure frequency. This controller will operate totally wrongly, so that the operation of the entire inverter will be very affected. What means that on the output, particularly for single line to ground faults, at the output we will have signals which are everything but not that what is supposed to have. Exactly. And then the system, this is collapsing. Just a challenge. Are these two issues decoupled? But I mean, that's very, very different approaches. If I try to explain to myself point number 1, in which I use Thevenin equivalent, in which I talk about short circuit capacity, I talk about exactly what is infinite bus. So we talk infinite bus is a strong grid, is the stone, and on the other hand, a weak grid is jelly. And so in this context, high fault current means stone, low fault current, which is also typical example at in the case of inverter connected, power electronics connected grid component generation. So then it's a jelly. So, but the second case has to do with the inverter operation, which is then creating significant problems. And it is also known that short circuit currents delivered by inverters are very negligible, are very small. And before you probably, you can give an answer, and then we'll ask Federico to, he's specialized for power electronics, that he ask his comment. So can you just comment this? My statement is these two things are very different, but contributing to instability, as a matter of fact.
I agree. Yes, those two things are very different. But I think if we want to look at system strength in terms of resilience of the system to withstand different voltage variations and not be stable in terms of voltage, we really need to think about not only short circuit capacity and the sensitivity on the of a bus bar or IBR to small changes in the system operation, but also to larger changes and what would happen if we have a fault. So we can really have the system operates great in steady state with small disturbances. We apply a fault, PLL does something completely different, we lose stability. Or we can have a different bus which has maybe higher short circuit capacity, but operates very differently in dynamic state. So we have those two aspects of system strength that I want to stress here, and we really need to think about both of them if we want to maintain stability in terms of voltage.
Thank you very much. I'll add even the level of harmonics could be also part of the definition what a strong or weak grid is. Excellent.
Yeah, you can look at it from power quality perspective too, and also, so I'm more here concerned with post-fault stability of it. But of course, you could have with lower system strength, you will also have more harmonics likely and things like that, which will affect normal operation power quality of the system. Yeah.
Great. Federico, please unmute yourself, and Federico is a professor from Skoltech. Please, Federico.
Yes, thank you, Alexander, for your presentation. Yes, I was looking the model that you were showing for the weak grids, mainly based on the Thevenin model, right? For the yes. And I was wondering, because this Thevenin model, you don't change, you don't affect the value of the frequency of the system. So and then you start discussing the frequency issues. So you consider the frequency changes in your weak grid model or not?
So here we're more concerned with voltage changes indeed, but here I mentioned frequency because I want to stress that PLL itself also needs to have accurate evaluation of frequency and voltage angle. And if it doesn't, and we have higher jumps in Rokov and voltage phase jumps, we can have the what they call like a full jump of IBR not being able to attach to the system frequency and voltage, and then you get even more disturbances happening afterwards. So in the sense, I'm mentioning frequency more in the sense that it is important for PLL and for IBRs to evaluate how a system operating.
But you don't change in your model the frequency.
No, we focus here on system strength, yes, on the short circuit capacity sense.
There is constant, the frequency, I mean, right? Or not, or I'm wrong?
Can you rephrase the question? I'm not
yes,
sure.
So my question is, in your Thevenin model, you didn't consider any, let's say, group control or anything, right? This is just from the perspective of the circuit.
Yeah, this is from the conceptual circuit perspective. Yes, of course. So if you apply different control strategies on the frequency side, you might help some of these issues, of course. But the main point here that I'm trying to bring is that we need to think of strength of the system, not just in steady state operation and sensitivity of voltage to small variations in current, but also operation of that same system if we have larger disturbance. And those things can very much differ in their response. We can have a system that is very strong in steady state, but if a fault happens, we have a lot of issues, which maybe we would not expect based on short circuit ratio. This is a paper that we wrote, and it was accepted for the conference coming up in a week from now in Singapore. So I'll be there if anyone is visiting.
No, I'll give a plenary talk. It's in
really?
Singapore.
Then we'll meet there. I'm flying in 2 days.
I'm fed up with traveling. Traveling today is not that easy from different countries.
So online.
Yes, online. I will. But Federico, it is assumed that the grid frequency is constant, and this simulation. But Aleksandar, have you done this simulation in Dixieland, or you just?
This is more conceptual. This is more conceptual. Yeah. This is what I'm talking about. More conceptual. But if you would do simulation, you would also, of course, need to. First, if you do simulation, you really need to think about what is your strong grid, because we don't have that in systems. That doesn't exist, and we used to be closer to that, but that's also a concept that's kind of losing its point.
I think that this slide is a very inspirational slide for a long debate, and I'm very happy that you open it, including Federico, including your supervisors. Actually, who is your main supervisor? Is it Marian or Jose?
Marian is the main promoter of my PhD, yes, but I also work with Jose. So Marian is more, let's say, protection expertise. Jose is more dynamics expertise. So I work kind of between those two. Yes.
Brilliant. One of my PhD degree students is working on short-term voltage stability. And he's still trying to understand the problem we already used, but you are using Dixieland. We are using PSCAD. We are going to using EMTP type of software, which is but you were focused on dynamics of load for this purpose and the load characterization, which does matter when it comes to voltage.
Exactly.
Dixieland was absolutely fine.
When
it comes now to that, what you are now showing number 2, then PSCAD is needed. Actually, in south of England, the problem of short-term voltage instability can arise, but in my personal opinion, as a result of number 2, and number 2, that's quite interesting. So we'll debate and we'll discuss. However, this slide number 44, I like it very much, particularly when you got extra spices from our operational power system protection, which should actually eliminate, not contribute to voltage instabilities.
Yeah, and we see more and more that it contributes occasionally, as we see in some blackouts and events where, protection just doesn't do what we're used to it doing. or not as fast.
But let me use this opportunity. You also talked about fault-induced delayed voltage recovery.
Yes.
That means we have a fault in a system when we have lots of motors, air conditioners particularly, and they stop.
Yep.
Then they drop a lot of reactive power, for example, 6 per unit instead
Yep.
of.
Correct. Yep.
Then the system is not recovering. The system is, I can say, tortured, voltage is low. And what is the remedial action? Power system protection. You disconnect this. This is an ordinary thing which is known to experienced protection people. So that's the measure. You disconnect these conditioners, voltage goes back, and everybody is happy. The problem is that it must be done on time, otherwise the system might go into voltage collapse.
Yeah, you also might see this more, which is something that we see that during those fault-induced delayed voltage recoveries, you lose some IBRs or DERs, either because they were not designed to follow that much deep voltage drop, or they in some ways do not manage to comply with those effects.
And for those who are attending and forgot what IBR is, it is inverter-based resource. It is power electronics connected generator, or so converter interface generator. These are many abbreviations, but in the United States they like IBR.
Yes, so I think we also use IBR in the upcoming working group that you mentioned for PSIGRA and IEEE, and I think that's the most common one. It kind of encompasses all the PV, wind type 3, etc. So you have some inverter that connects it to the grid, which is most important part in terms of operation from the grid perspective, at least.
Yes, but inverter is in double-fed induction generator. It's not inverter. You have inverter, but it
you have partly.
Not only, you have also
direct coupling.
Things. Yeah. So then I personally would use converter interface generation. It is used in the paper 2020, where Jovica and Nikos and the group of authors defined the new stability aspects in the grid.
we had a big discussion on the working group about IBR or CIG.
Well, but we know what we are engineers. We know what we are talking about.
Yeah, we call it differently.
Sorry for such a long break. I was really inspired. Federico, we'll continue this conversation, which is very important. And please move forward, Aleksandar.
No, I don't know how much time I have. I still have quite a lot of slides.
You have enough time.
Let's see. Okay, so what I wanted to stress here and what our paper that I'm going to present to Singapore really focuses on is that we need to classify this better. We need to think of system strength in different ways. So we see that system stability, we have very clear classification. As I mentioned, those 5 types, we have them also in steady state and dynamic state, but system strength remains without a consensus. So what we try here, we try to introduce a clearer classification, and we think that this is important because it presents a framework how we can think about novel methods and better evaluation methods that can capture some of the things that I've been discussing. So what we propose is to have system strength split into steady state system strength and dynamic state system strength. And then if you talk about steady state system strength, you would talk about what many call now related to voltage sensitivity. So you would think about short circuit capacity, you think about steady state operation, you think about small disturbances, linear operation. So you can do Thevenin impedance equivalence, but you also need to consider loads. You need to consider PLL parameters in very weak grids, because sometimes even if your grid is in static voltage sense stable, maybe your PLL parameters will not allow it to operate stable. You need to think about other short circuit support like synchronous condensers, and generally this can be typically modeled well enough by RMS models, a bit advanced RMS sometimes, except if you have very weak grid model. So this is one aspect of system strength the way we see it. So operation near nominal voltage, small disturbances. And the other part is the one we just talked about, dynamic operation, dynamic state system strength. So here we really need to think about operation under transients, under large disturbances. There is no more Thevenin equivalence here, it's nonlinear. We need to think of it differently and not model it in such a way because it's not going to reflect what actually is going to happen in the grid. We need to think about converters being saturated. We need to think about faults right through and interactions with the voltage dynamics, such as load dynamics we just talked about, control loops, And we also need to keep in mind that protection might not operate as fast as or as accurate as we are used to it. And for these events, we typically need very advanced RMS models or EMT models, of course. So we see this classification very much in line with the stability definitions, because we have on one side steady state, on the other side dynamic state. But if you want to focus on evaluating them, you really need very different approach for evaluating is your system strong in steady state or in dynamic state. There's more details in the paper that will be, I think, soon available on IEEE on this. But some conclusions in that sense would be that system strength is really a term with various and evolving meanings throughout the world, and we really need to think about consolidating this across the academia and industry. We introduce a classification here where we split it into steady and dynamic state system strength, and then we want to use that to make better methods that can evaluate how strong our system is in both terms. So we see that higher penetration leads to many challenges, and we also see that we need different or tailored evaluation methods to see different challenges in steady and dynamic state. For steady state, there are many methods already existing. I mentioned some, short circuit ratio and similar ones, but they're generally not well suited for renewable dominated grids yet. That is something we work on it still. Hopefully we'll have some output on this as well. I'm working on a new method that might reflect this a bit better, but I still need to do some more work there. And also we need to think about methods that focus on dynamic state system strength. So can we somehow quantify how the system will behave in terms of its strength in dynamic response? And that is a bit of a more, let's say, challenging task, but it's a really different perspective from the steady state strength. And that is also something that we work on. So that was a part of system strength. I also have one more part, maybe 5 or 6 slides. I don't know if we have time.
Yes, yes.
Yeah, so now I'm more talking about, so we talked about steady state and dynamic state system strength. This is more approach for dynamic state system strength. So if I come back to this slide, if you remember, what we can do on one side, we can measure system strength to predict voltage issues. That is what I've been talking about until now. Or what we can also do is we can evaluate symptoms. So what if we don't try to evaluate system strength, but we try to evaluate directly the symptoms we would get from these faults, either with many offline simulations, and then we can figure out which parts of the grid may be weaker in terms of fault behavior, or maybe with the real-time operation with PMUs and wide area measurements. So this part is more on the symptoms evaluation. So if you think of severe short-term voltage deviations, not just short-term voltage stability. First, you have short-term voltage stability that we just talked about, which is generally occurring in grid sections with a lot of dynamic load, everything we discussed, and generally it happens very fast and you have a voltage collapse in some way. This is just an example. It can look very different, of course. Another instability mechanism that you see in short term is transient rotor angle instability. Very different physically, because it happens in when you have large rotor angle deviations, there are lots of synchronism. But if you look at it from what happens with the voltage, you will also see very, very strong voltage deviations in the first 10 seconds of the event. Then you have the fault-induced delayed voltage recovery, that we also mentioned, which happens where you have a massive stalling of induction motors, and generally you have delayed voltage recovery, sometimes a peak afterwards, which is not on itself instability, but it can lead to cascading or instability. And in the end, you have something more appearing nowadays, which is converter-driven slow interactions instability, where you have remote areas or weak grid sections with low system strength. And there you might have interactions between IBR controls grid or in between them, or also with the synchronous generators. And you may see oscillations, sometimes from 7 to 10 Hertz, but also in other frequency ranges. Generally, subsynchronous oscillations may occur. So these are, let's say, 4 different voltage deviations we might experience that may lead to short-term instabilities. So this approach more goes into what do they all have in common. So we know that all of them are initiated by a fault or a large voltage dip. They generally manifest in a short time scale, up to 10 seconds. They all lead to significantly disturbed but very distinctive post-fault voltage deviations. They tend to interact with each other. So if we see a instability happening, it will also often be a combination of these, not just one of them. And they happen to be more common or more severe when we have more IBRs or less synchronous generation in the system. And of course, this may lead to cascade. So the idea here is, can we create some kind of a unified approach that can tell us how bad really the event is that is happening, that is taking place, how bad that event is. So if you look at the quantification methods now, state of the art, most of them focus on binary evaluation. So is an event stable or not? But the ability to quantify how bad the event is also needed, because we sometimes see the event either in simulations or in real systems, and it's very hard to tell by some kind of a number or a metric how bad this voltage deviation is. You have only, engineer can have a look at it and tell you, okay, this is bad or this is not bad, but you don't have a number that tells you that. So some numbers exist, of course. There is a transient voltage severity index that basically measures the time duration that the voltage is under certain threshold and how much under the threshold that you can calculate. But we wanted to try to improve that. So we want something that is able to detect and quantify severity of different deviations, that can work in both conventional and converted dominated systems. We want it to be intuitive, adaptable. We want it to be simple and computationally efficient, because we want to apply this either fast in real time, or we want to apply it to a lot of offline simulations in an automatic manner. And we wanted to provide potentially real-time insights. So can we do something better than transient voltage severity index, basically? So we developed here methodology that we want to evaluate this in a bit more, let's say, relevant manner. So we developed something we call cumulative voltage deviation metric, where we basically measure not just the under voltage deviations, and not just in a very simple constant way, but we measure them with kind of an envelope, and we measure how much does the voltage after fault deviate under or over this envelope. We translate that into voltage deviation chart, where we can evaluate how that deviation progresses over time, how much of it is under voltage and how much is over voltage. And it is always applied after we see a large disturbance, so large voltage drop. And what is important here with this linear threshold that is, let's say, converging more as the time passes by, more weight, we give more weight to later voltage deviations. So if you have a voltage deviation here, it will be calculated as less weight than here, because you already have here your threshold is increasing. So if you have a voltage deviation here, you know that voltage deviation after that much after fault is likely more correlated to potential instability, because the voltage still hasn't recovered after several seconds of the post-fault behavior. So if you calculate this index of this total deviation, the larger the index is, it gives you a higher chance of various instabilities, potential disconnections, or cascading risks. So this doesn't tell you exactly if the system is stable or not, but it gives you a clear number that tells you how bad your voltage deviation is. And we want to apply that in a more probabilistic manner, where we would run thousands of simulations on a system with different operating conditions, and you would say, okay, this bus bar, if we apply these types of faults with these controls, we see very high voltage deviations. So that gives us an idea of the dynamic system strength in a way. So it tells us that the system may not be operating that stably in that manner. And then we can look at those specific buses or cases where we found that the issue may be pronounced. And in those cases, we can apply more detail, maybe EMT models or something, and really find out what is happening. So this would be more of a screening method to find where we may encounter more dynamic issues. So we did some models and testing to see how this behaves. So again, we used the similar test system as before with DERs and dynamic load models. We did everything in the Power Factory again. We did everything with Python. It's here very important that we are able to model many different cases with many different parameters. We talked about how different parameters may affect this operation very differently, like different control strategies, different penetration of different loads, etc. So we really need to be able to go through many cases fast, which manually is simply not feasible. So we run numerous dynamic simulations, and then we see how this method performs. So what we did is we ran many cases and compared cumulative voltage deviation and the transient voltage severity index. We did it for several different types of voltage deviations. And first, we have here 25 different cases of fault-induced delayed voltage recovery. The red one presents the least severe one, and then we increase severity by increasing the number of motor stalling or the penetration of dynamic load in general. And then we try to quantify that with these two metrics. And what we see here, if we use transient voltage severity index, we see that it inaccurately tells us that this case is the worst in terms of how bad the voltage deviation is, that it gets better afterwards, but we know that's not the case. However, we see that the metric we introduce gives a much better operation here, and we can tell clearly that the further we go with our scenarios, the worse the case gets. So we're able to quantify this. In the different simulations, we also simulate oscillations with different amplitudes, with different frequencies, and we see a very similar effect. We see very low sensitivity on TVSI, but much better sensitivity for our method. And we do something with a bit more combined instability. I mentioned that often these cases can be also intertwined, these instabilities. So we model fault-induced delayed voltage recovery that leads to rotor angle instability. And again, we see much better operation here in terms of quantifying these events. So let me see what I have here. Yeah. So the idea is that we can give a number that really tells us through our simulations, or maybe in a real-time operation, how bad is the event that is taking place and how much our voltage is deviating from the normal operation. And if we know that characteristic, we can then design systems or control them in a way to avoid these dynamics. So that is also a very recent paper, and we're now working on a journal paper that continues on this. And yeah, with that, I think this is the last slide. So overview of the whole presentation and some conclusions. So what we see and witness is an unprecedented revolution in power systems. We see proliferation of renewables everywhere. We see also the many methods and approaches we use to define and evaluate the risk of cascading and instabilities in conventional systems either have to be adapted in some way or maybe completely overhauled. So let's say the approaches that we used to use are not always applicable anymore, and we really need to think how we can make them applicable for renewable-driven grids. We see the systems becoming more vulnerable in various aspects. I talked about short-term voltage stability and system strength, but also we have inertia and issues related to that. My work is mainly on this part, but we see systems becoming more vulnerable in terms of cascading faults from various aspects. My thinking here is that we really have to approach this issue from these different aspects. We need to think about which factors play the most important role here. Think of proliferation of DERs, different controls, dynamic loads, something that I talked about in the beginning of the presentation, how that may affect the performance of the system. We need to really think, what is system strength? How do we define it? How do we classify it? How do we measure it? How do we evaluate it to ensure that systems are operating stably? And how do we do that for both steady state and dynamic state? Because yeah, every system is as strong as its weakest link is. And if we design systems to operate very well in steady state, but then a fault occurs and we have a lot of cascading, that's not good. So we need to be able to preserve system resilience in both steady state and dynamic state operation. And of course, we must ensure the system resilience remains high, so we avoid ultimately or minimize cascading faults. It's likely that we will get more of them, but we can do our best to reduce their effect. So what is very important is the systems used to be more self-correcting. You had more inertia, you had more system strength. So if an event occurs, disturbance occurs, we have kinetic energy stored in generators. We have a high short circuit capacity of generators. They provide short circuit current. We don't have any of that anymore, not that much at least, and we're going to have less and less of that. So instead of letting system self-correct, what it used to do, we really need to steer it. We need to control it away from cascading faults and instabilities. That can be done in many ways, of course. Some of the promising ways are using wide area applications, using PMUs, etc. But of course, we still need to do a lot of work on this part. So I don't have all the answers, as I mentioned, but I hope I gave you some ideas and some food for thought. With that, I would like to thank you for your attention. And if you have any more questions, if we still have time, of course, feel free to ask. And yeah, you can always contact me, as you see on the left side. And yeah, as I mentioned, this work is part of a larger project which is supported by Dutch Scientific Council and a lot of companies in the Netherlands. Thank you.
Thank you very much, Aleksandar, for your exceptionally interesting presentation. Last time we had something what had to do with the assessment of situational awareness of active distribution networks. Today we talked about short-term voltage stability or instability, the nature, the ways how to detect, how to evaluate, how to quantify, how to understand. I believe that from the audience we have some questions, so feel free to raise your hand or to write the question down in a chat, and be active and proactive, please. Questions, please.
Hello, Aleksandar.
It is Joe Young, Dean, Assistant Professor from Shandong University. Please, Joe Young.
Pleasure.
Okay, first, thank you very much for giving us this amazing presentation. It is amazing in terms of both quantity and quality of the work. Especially the most wonderful part of this presentation is that you proposed dynamic assessment, assessment of the dynamic voltage stability, right? Actually, I'm wondering if there's any, I don't know, the correlation between static voltage stability and dynamic voltage stability. As you mentioned, there might be a system which is dynamically weak but statically strong, or vice versa. Of course, if we use a traditional short circuit ratio, of course, it is not correct, and the correlation might be very weak. But recently, some researchers have proposed the so-called generalized short circuit ratio, especially Professor Xin Huanghai from Zhejiang University. But for his work, he considers the renewable energy, but he also assessed the static voltage stability. I mean, in terms of small signal stability of the voltage. I'm not sure if there's any correlation between this kind of generalized short circuit ratio, which is considered for the static voltage stability, and your proposed dynamic voltage stability.
That's a great question. The generalized short circuit ratio you talk about, I'm aware of it. I also mentioned in that paper that talked about system strength, and of course it does help evaluate better the small signal stability part. On the other hand, if I remember correctly, it is also focused on a single IBR to the system approach. So you have multiple IBRs, it gets very complicated to make that entire short circuit ratio work. It's possible, of course, but it gets more complex and complex. And the other thing that is very important there is that, again, you're also only focusing on small signal stability. So you are able to linearize the model because you're dealing with small disturbances. But that, again, will not tell you much about dynamic state operations. So yes, it helps in some ways. And I really like that metric. It's really good, I think. But I still think there is room for improvement, how we can apply that on a more broad scale system as well, and how we can maybe not just evaluate on steady state, but on dynamic state as well. Are they always correlated? Depends. There are cases where you really have that low short circuit ratio really tells you there might be issues here in dynamics too, but you also have very opposite, where you see a study, and I think there was something in Ireland where they did a correlation between short circuit ratio and I think critical clearing time or something for IBRs, and you could see the correlation was all over the place. So it couldn't really tell you where you might experience issues that easily. So it depends. It depends really.
Yeah, it might depends on the types of dynamic load that we use and the
also
proportion,
yes. Yeah.
Okay. Thank you very much.
Thank you for the question.
Okay.
Excellent. Thanks. Further comments from the audience? Jihao Wang, please.
Yeah, thank you, Alexander. I have two questions, and the first question is that maybe in the second section, the simulation result shows that if the DER has the ability to run through a fault, in that situation, more DER and the more stable of the system. I want to know that what's the simulation like that. If you apply more DER, will the DER replace the synchronous generation, or you just add some additional DER into the system so you get the conclusion?
Yeah, no, this is a good question. In that study, we did it as a replacement. So if you would have, let's say, 1 gigawatt of synchronous generation, if you have 10% DER penetration, we would replace 100 megawatts with DER. So more, let's say, more realistic in that sense that we want to have systems that slowly shift towards renewable-driven generation. You could, of course, model it as an addition as well, but then you would likely see less issues. And that is maybe not as realistic, because as we see more renewables being put into the grid, we also see less synchronous generation being operated.
So if the with more DER and less synchronous generation, how the system gonna be more stable? In my opinion, the DER have less ability to support the grid than the synchronous generator. So why it has the positive effect to the grid?
It has positive effect because of its location. It's located very close to the load centers, and then if you have a dynamic support in terms of reactive power, it's very localized support, and then you can tame the voltage deviations induced by dynamic loads better compared to like some centralized generator. So that can help.
Okay, thank you, very clear. And the second question is that about the FCR, and the FCR is based on the top Thevenin equivalent model, and it's very easy to use in the practice. But the you see the TCRI, and I don't remember it. It's based on the simulation result. So you need to simulate all the force and disturbance so that you can get the index. I think it's much harder to use in practice. We have some much more simplified index in futures like the SCR, but we consider the non-linearity or the dynamic. What's your opinion about it?
So I agree. So what really made short circuit ratio applicable everywhere is very simple. You can calculate it very simply. You need very simple models. You can do it even by hand if you know information well, and that worked well for a long time because we had synchronous generators that really behaved very close to that model. So we could say that is relatively correct. That was never entirely correct, because even impedance of synchronous generator changes during the fault. You have you have the transient one or the sub-transient one, but it was close enough that we could say, okay, this is a reasonable approach that we can tell how strong our grid is. However, as we move more towards IBR operation, the short circuit ratio becomes less and less applicable. We see it's less and less informative. And I agree that for once we need a bit better approach than short circuit ratio. For instance, generalized short circuit ratio is an improvement in the right direction, but there are still a lot of aspects around it we need to improve. But on the other side, for as you mentioned, for simulation approach, I think that's also going to play a big role, as we cannot. So if you want to mathematically evaluate how systems will behave in terms of post-fault behavior, like in terms of after fault what happens, it gets really complicated to make like a metric or a model that will tell you that without actually simulating it. So I think we will need to shift more towards simulation-based approaches, and we see computational power increasing a lot. We see that we have automatization being able to run simulations very fast. So my idea of how we can do it in the future is we can run a large number of simulations with very likely parameters with some uncertainty modeling around that. We can tell which parts of the grid may be more likely to experience instabilities, and then we can analyze those small sections instead of the whole grid in a very detailed manner. That's
at least
how,
we
that's how
can
I
use
see
the
it.
index based on the simulation result to estimate the stability.
Yes,
maybe in
yes.
future we will have much more better index in future. Okay,
Yeah.
thank you. That's my
You're welcome.
question. Okay, thank you.
You're welcome. You also see some approaches like, I think Australia already has like whole grid or a part of grid EMT. So they can like simulate a lot of things in it. They will whole grid and model like that. But again, if they want to run different scenarios in different variations, it gets too slow and in time perspective, not really feasible.
Yeah. Okay.
Thank you, Jihao. Further questions from the audience? In the meantime, I can ask a question, a very formal one. We are talking about short-term voltage stability. We also talk, and we know that there is a problem of long-term voltage stability.
Yep.
When we talk about long-term voltage stability, which time constants we are linking to this problem?
Tens of seconds, minutes. So
how about short-term? Okay, how about short-term voltage stability?
Less than 10 seconds typically. So it can be much depending on the event you focus on, but they're generally not longer than 10 seconds. It can be if you talk about some very fast control aspects, it can be less than a second, but there you cannot do much anyway. So I would say 1 to 10 seconds in most of these events that we talk about.
Okay, from this understanding, from the perspective of understanding dynamic simulation of short-term voltage stability, are RMS-based software packages appropriate, or we should go to EMTP type?
I would say the RMS models are also getting much better. So for instance, if you look at what EPRI is doing with RMS models, they're making a lot of what they call performance-based models, or very a bit of a simplified EMT models into RMS environment. So I would not say that RMS itself is too much of a limitation. So you can still do a lot with RMS, but if you want to go to some transients that you simply cannot see with RMS, such as some different frequencies, maybe really fast interactions and controls, etc., then you need to move to EMT. So I would say we need both, because we cannot do EMT on a very large grid. So my vision is to have RMS tell us from this much problem, get to this, and then do EMT on that.
I like your answer, and it's true. From the perspective of load modeling, my understanding is that your PhD degree is linked to load modeling, short-term voltage instability.
Yeah, short-term voltage stability, system strength, applications of different load models. Yeah.
Yes. Are you aware about transient recovery voltage load model?
Transient recovery voltage load model.
Okay, maybe not. Okay. It's about the characterization of load.
Okay.
And we understand that we have frequency-dependent load models, voltage-dependent load models. I think that in this case, we are more focused on voltage-dependent load models.
Yep.
We have constant power, constant impedance, constant current.
Yeah, those are the basic ones.
Composite, yes.
Yeah. You have also.
Yes, please.
Different approaches. You have different approaches there. Also, there is also an approach from university in Belgium, Liège, where Thierry van Kliksem also has some approach for modeling of loads more from probabilistic perspective. There was also a PhD on that recently. So there are different ways to tackle it. I think the composite load model that I used is a really good balance between dynamics you can capture and how complex it is to use it and model it. So it depends again what you model in the end. There is a spectrum there, of course, what you can apply. But I think for the simulations and for things that I'm here exploring, I think this one is the most applicable, I would say.
Well, if I would be let's say, tough reviewer of your thesis or your paper, I would challenge you with the transient recovery voltage model. What means?
I will have a look.
TRV, transient voltage recovery or something like that. So it's a PhD degree thesis of one of my former PhD degree students, in which, look, when we think and discuss about load very quickly, we have a motor. And if we want to model this load, the complete model would be actually the whole full model of the motor.
Yeah, it's very complicated. Yeah.
7th order. So it's not sensible. Differential equations. So I'm talking about dynamic models in which we have differential equation, which is description of load behavior. And when we have a fault, the response of motor-based loads is such that we have a drop of active power and then slow exponential recovery. Sorry, exponential recovery model. So an exponentially we have increase of active power. So this dynamics is related to active power, but also to reactive power. So that's one of models. Sorry, it's not transient recovery voltage. This is exponential recovery load model. Exponential recovery.
I'll find it.
Based on our real data which we received from network, we also saw that some load models, I mean, the behavior of load is such that there is this exponential recovery component, but also superimposed oscillatory component.
Yeah.
It means that it's now second order, differential equation of second order. So I'll feel free to send you one or two references that's which you might consider from the perspective of load modeling and characterization of loads, what is important for understanding of load, short-term voltage instability. But
yes,
now,
please do.
Yeah, you talked about steady state stability.
Okay.
Steady state and dynamic. Yes.
Okay.
I had one small issue, but let me challenge you with the following question. Steady state, isn't this problem related to long-term voltage stability, whereas dynamics is related to short-term?
I would say yes, but also I would also say steady state. Yeah, depends from which definition perspective you look at it. I see steady state as small disturbance instability, but it can be also in a long-term operation, of course. Yeah.
But so I cannot link small disturbances with short-term voltage instability. I'll tell you why. Because
I agree.
In this context, because if you have small disturbances, that means you slowly increase load, you increase, and then you reach instability. But this is typical.
That's long-term.
Long-term.
I'm not saying that steady state system strength is related to short-term voltage stability necessarily. It's more dynamic state. I agree.
Okay, a very good point. Well, I think that we could have further discussions because for the whole audience, short-term voltage instability or stability, first understanding the nature, it's not easy.
It's very complex.
Number two, ways for monitoring of this phenomenon. We are aware that colleagues from Arizona State used the Lyapunov theory and Lyapunov index. Now it's not in my mind.
Yeah, maximum Lyapunov or minimum. Yeah, I know what you mean.
Maximum coefficient. I forgot. And then colleagues from Tsinghua have improved this approach. However, both of them haven't gone deep enough into the robustness of the approach in which these are two parameters of this methodology. There's some small epsilons, which, if not properly selected, the methodology can be quite complicated to be applied. Also, pre-filtering and post-filtering should be applied to make the output of maximum Lyapunov exponent based approach, maximum Lyapunov exponent based approach to make it practical. And I hope that finally my PhD degree student will focus on the paper which we are writing. That's my personal experience. I worked with National Grid on this project on Southeast problem, which is related to high penetration of renewables, including interconnector, which is also HVDC, and subject to short circuit of one substation, London could experience short-term voltage instability, and it's a long ring topology, and this problem is, that's why this problem is very important. However, the nature of this problem has not been fully discovered, and in this context, I think that this instability in this southeast region of UK is caused by instability caused by PLL and converter controller, but not in this sense like slowly degrading.
No, it's more of a fast, like those are HVD, like similar to those HVDC instabilities that are very fast. Yeah.
Yes, yes.
Yeah, there's we see more and more different issues appearing also. So.
Yes. Anyway, Aleksandar, from my side, that's it. We're gonna discuss and talk.
I've never eaten it like this.
Also, your supervisors, also including our work in SIGRE. I joined IEEE SIGRE working group. So from my side, thanks. Would you like to check with the audience if there is any question, or if not, that you arrange a session to make a joint photograph, whereas you can, Aleksandar, please stop sharing the screen, your presentation.
Yes, thank you, Professor. I think there's no more questions. And because I have another project meeting in 10 minutes, so I I think we should close the session now.
Yes, so can you make a photograph, and
Yes.
Aleksandar, can you stop sharing the screen?
Yes.
One more. Or maybe it has already been stopped.
Aleksandar, can you stop sharing the screen? I don't know how to. Oh, okay. I know how to close it. Okay.
It's good. Brilliant.
So now I'm asking all the audience, if you have the camera, please turn it on, and we will take a joint photograph. Thank you. 请大家打开摄像头，谢谢。Hello, Mustafa.
Yeah, good. Thank you.
Hi, Anna. Здравствуйте. Hello, Stepan. Как вы, Stepan?
Thank you, Professor. I'm fine.
Etienne, Yonti, very good. Prof. Martin, Ibanez, Federico.
Okay.
You can count down.
Sorry?
You can count down and make a photograph.
Okay, okay. I will now take a photograph. 3, 2, 1. Okay, I've taken the photograph. Thank you very much.
So thank you very much to everybody. Thank you very much, particularly to Aleksandar Boričić from Technical University of Delft for delivering such an exciting and interesting presentation. I must admit that this is a topic which I really like, which is linking power electronics and power systems. And this is really very interesting. This is an ongoing topic. This is a topic trying to be addressed and understood for IEEE and SIGRE working groups. In my opinion, those who are specialized for long-term voltage instability cannot that easily understand short-term voltage because they're biased. And we need
very different.
more, and we need more Federicos, those who are coming from power electronics world, to help us, because we are totally biased in our world. We need fast transient process assessment and so on. So let's express our thanks through applause to Aleksandar, and then have a good rest of the day. Goodbye to everybody. Do widzenia, do свидания, zaidzień.
Thank you very much for having me. It was a pleasure.
Bye bye.
Bye bye.
Thank you and goodbye.
Bye.
Bye bye.